So this is going to be the first part of the chapter 6, which is about the normal distribution. And this is something that we're going to kind of come back to a lot throughout the rest of the course because one of the main things that we're going to talk about in this stats course is how to deal with situations that are normally distributed. So quick little review about what we mean by normal distribution. So, normal distribution is made up of the following things. It's basically tracking a random variable, which remember is a variable that can take many different values depending on what happens in a situation. It is a type of probability distribution, which simply means that it's a way of representing the probability of this random variable. So how likely is it that this random variable ends up being 5, or ends up being 10, or ends up being negative 1.6, depending on what you're tracking. And then it can deal with either discrete or continuous. So discrete random variable is one that has a finite number of values. A continuous random variable is something that has infinitely many values to put, again, elementary wise. That's the kind of basic difference. The way we said it way back when, because we actually talked about these before, is discrete is something that you count, continuous is something that you have to measure. That's the difference between those types of variables. So probability, a normal distribution is something called a density curve. So what we mean by a density curve, and this is where it gets a little bit weird for some of you, but try to stick with me here. A density curve basically means that the total area under the curve is 1. So if this is my normal distribution curve, that means the area under this curve, the amount of space under this curve is equal to 1. And thus we treat that as like the probability. So think about the area under the curve as the probability of an event happening between this and that. So for instance, if I were to mark off, say, the area between -1 and 0, this area right here, that would be the probability of this random variable being between -1 to 0. So the area under this curve is the probability that the random variable actually is somewhere under this curve, or is somewhere between these two values there. Um, some rules about this density curve is that every point must have a vertical height that's greater than 0, which basically means that it does not touch the x-axis. And again, the probability, or the area under this curve must be equal to exactly 1. Um, Now, this middle number right here, this is usually what the average is. So in this case, the average of whatever random variable this is seems to be 0. But this is where your average would go. So the middle of your curve is usually your average value. And then each time you jump over, that's one deviation. So this would be one deviation, this would be two deviations, this would be three deviations, and then this would be -1 deviation, -2 deviations, -3 deviations. So this, whatever random variable this is, it seems like the average value of whatever this is tracking is 0, and the plus or minus of it is basically 1. So this is 0, 1 deviation, so it's +1, 2 deviations, so it's +2. If my deviation, let's say my deviation ended up being for this random variable 6 for some reason, then this would end up being 0 as my average, and then this would be 6, this would be 12, this would be 18, because it's 1 deviation, 2 deviations, 3 deviations. So again, these numbers aren't always going to be 0, 1, 2, 3. It's going to be the average, and then they're going to jump by 1 deviation each time as they go left and right. Now, one I guess result from this is that you could have what's called a uniform distribution. So I'm going to talk about this briefly before I get to the normal curve, because this will kind of set the stage there. So a uniform distribution is basically like a quote-unquote curve where every single chance for every single variable is equal. So for instance, this uniform distribution here might be the chance of rolling a 1, 2, 3, 4, 5, or 6 on a die. Because the chance of rolling a 1, 2, 3, 4, 5, 6 on a standard 6-sided die are all the same. They're each 1/6. So if I were to track its probability curve, it would end up being one big rectangle essentially, because the probability of getting 1 is the same as probability of getting 2, is the same as probability of getting 3, 4, and 5, and 6. Now obviously you can't get 1.5, so the in-between numbers are a little bit weird, but I'm just using it as sort of an example here. So if your probability quote-unquote curve, so if it doesn't come out to be a bell curve like this, that's called a bell curve. If it's not this and it's more rectangular, that means it's more uniform than normal essentially. So let's see how we can use this uniform curve to figure out probabilities, and then we can apply that to the normal curve coming up here. So it says the stats class has class length, so how long the class takes, that are uniformly distributed between 50 and 52 minutes. So that means that on this little curve here, let's say this is where the 50 mark is, and this is where the 52 mark is. That means the class is equally likely to last as long as it's between these two values here. So the chance of it lasting 50 minutes is the same as the chance of it lasting 51 minutes, is the same as the chance of lasting 52 minutes, is the same as the chances last. Sorry, I'm getting tongue tied here. Let me try that again. The chance of lasting 50-minute class period is the same as the chance of it lasting a 52-minute class period, which is the same as it lasting the chance of a 50.25-minute class period. So every possible time it could last is somewhere between 50 and 52 minutes, and they're all equally likely to happen. That's what, again, uniform means. So it says Kim here has a job interview immediately following her stats class. If the class runs longer than 51.5 minutes, so Kim has to get to a job interview. If her class is longer than 51.5 minutes, she'll be late. So what's the chance that her class is longer than 51.5 minutes? Because she doesn't want to be late, obviously. So what we need to remember here is that the area under this curve, because it is a density curve, it's a uniform, but it is a density curve because it represents the probability of a situation. The area under this curve has to be equal to 1. Now, again, it's not really a quote-unquote curve, but we call it a curve in math just because it's a graph, essentially. So don't get hung up on the word curve here. So because the area under this figure has to be equal to 1, we can actually figure out what the dimensions of this are, because this is one big rectangle, right? So if I know that the area has to be equal to 1, and I know that it goes from 50 to 52 minutes, well, that means that the length of this rectangle is essentially 2, right? 50 plus 2 is 52. Now, doing some basic geometry here, the area of a rectangle is length times width, or base times height, if you called it that. So that means that the area of this rectangle, if the length is 2, is 2 times w. And I know that the area has to be equal to 1. So area is 1, 2 times w, which means that the width, if I do some basic algebra here and solve for w by dividing by 2 on both sides, the width has to be 0.5. So that has to be 0.5. So now I have this rectangle set up. Now I can actually figure out the answer to the question here, because remember, in a density curve, area is the same as probability. So if I know that the area is 1, let me erase this here so to give myself some room. Come on, there we go. There we go. So I know that the area is 1. I'm going to write that here as a reminder. That means if I want the chance that it runs longer than 51.5 minutes, well, let's say right here is 51.5 minutes. We'll say roughly 51.5. That means I want the chance that the time of the class runs somewhere in this area, right? From 51.5 to 52, because this is the area in which she's late to class. So this is the late, and this is okay. So she's okay to get to her job interview if it's within this area. She's going to be late if it's within this area, because 51.5 is the cutoff zone, right? So if I want the probability that she's late, I simply need to find the area of this new smaller rectangle, which again I can do because I know that its height is 0.5, 51 to 52, or sorry, 51.5 to 52 is also 0.5, right? That's a 0.5 distance from 51.5 to 52. So this rectangle is simply, the area of it is simply length 0.5 times width 0.5, and we should know that 0.5 times 0.5 ends up being 0.25, which if we translate it to a probability or a percent is 25%. There's a 25% chance that she's going to be late to her job interview if her class has this layout to it. So again, the idea here is that density curves, both uniform and normal, are a way to represent probability as a geometric area. And then because we can represent it as a geometric area, we can use geometry tactics to figure out these problems that would normally be quite hard and difficult. Because if I didn't have this geometric aspect, figuring out what's the chance that it runs longer than 51.5 minutes is going to be kind of difficult because, yeah, I know that each time period has the same chance of occurring, but I don't really know what that chance is individually, so it gets kind of weird and again, almost impossible. Because the thing here to note is that if using a density curve like this, it's impossible, quote unquote, to figure out the chance that the class lasts, say, 51 minutes exactly. If I say, what's the chance the class lasts exactly 51 minutes? Well, okay, let's say here's 51. Where's my rectangle? If it's exactly 51, I don't really have a rectangle to work with. I just have a line, and I can't figure out the area of a line because the area of a line, or the line, is a one-dimensional object. It has no width. It just has a length. So this type of stuff can only be solved if you have a range of values you want to check for. So if I asked what's the chance that the class runs between 50.5 and 51.5 minutes, then I could do that. So normally what we would do here is that since we can't figure out exact values, if we want an exact value like the chance that the class runs exactly 51 minutes, we usually pick a very small time frame around that, like 51.5 to 50.5, and figure out the chance of it lasting within that time period. And since if we make that time frame small enough to be close to 51, it would be a decent enough estimate. Those that remember calculus, that somehow kind of relates to limits, if you remember, but we won't go into that detail right now. Now, what about if it's not a uniform distribution? What about if it's a normal curve, which is what this is? Let me get my pen off here. Let me see if I can't. Okay, didn't want to do that. I was thinking I can. Let me try something here. I was thinking if I can make that bigger. There we go. So I'm just going to blow this up here real quick. So this is the normal curve. It's a bell curve. Remember, the bell curve means it's normal because you have a high amount of people that are average, a low amount of people that are below average, and a low amount of people that are above average. So the average, because the name average means most, or not most, but typical, most people are typical in most areas. You have a very few people that are very on the high end, and you have even fewer people that are very high end, and then you have a few people that are on the low end, and very few people that are on the very low end. The best way I can describe this is think about heights. Most people are around a typical height range. Then you have a very few amount of tall people and a very few amount of very, very tall people. And then you have a few amount of short people and a very, very few amount of short people. So that's where this probability curve comes in. And this happens with most things in life, or most things can at least be approximated using this tactic here. But this is not a rectangle, clearly. So it's kind of hard to figure out the area under the curve when it's really actually a curve, because there's no basic geometry we can do here. So we have a table of values to help us out here. So table A2, which I'll throw up here in a second in your book, if you're using the same book I am. If you're not, then obviously it's not, but you can find this online. This is a z-score table. So if you want to Google z-score table, this is exactly what we're talking about here. And basically, what it is a table of values, kind of like a slide rule for those of you that are way old and remember logarithms and all that. It's basically a table that tells you what the area under the curve is for certain deviations. So for instance, let me go back to my big view here just so I can write. Remember, in a normal curve, it's split up in terms of average and deviations. So for instance, a normal curve might look something like this. Here's my curve. Very bad curve, I know. In fact, it's so bad I'm going to try it again. In fact, actually, I'm going to make use of my tools here and do it like this. I'm just going to use the one I drew. So I'm going to blow this up on screen here and then go back till it's even bigger and I can actually write on it. Sorry for all the screen switching, but it's just something I have to do. So if this was a normal curve, let's say, again, we're tracking heights just because that's what people can relate to here, height. I'm sorry if that is misspelled here. So let's say that the average height of the average American male is somewhere around, I don't know, 5.5 feet. So this would be where the center is, 5.5 feet. So it wouldn't be 0. It'd be centered at 5.5 feet because that's my average value. And let's say the deviation, so the average was 5.5 feet. Let's say the deviation for the average American male's height is plus or minus zero point 0.2 feet. So we'll say that the average American is 5.5 feet high, give or take zero point 0.2 feet. So the deviation is 0.2 feet. So the way I would write this curve is that it would be 5.5 feet here, and then this next mark would be one deviation away. So it'd be 5. And it's going higher, so it'd be 5.7. Because again, it'd be one deviation up, so plus one deviation, or in this case 0.2, because that's what the deviation is. And then the next one would be two deviations from the average. So this would be 5.9, because that would be plus another deviation. So 5.7 plus 0.2 is 5.9. And then the last one that's usually marked is the third deviation up, so this would be 6.1. And then it keeps going, but we usually only mark 3 up and 3 down. That's very typical about how it's written there. And then we'd obviously do the low end too. So this would be deviations down. So if this is 5.5 feet, one deviation below that would be 5.3. Because in this case, I subtract a deviation, which means I'm subtracting 0.2. So again, you're not jumping by one, you're jumping by one deviation. And this is usually either given to you or you're given information that you can figure it out, because we have figured out standard deviations before. But usually for now, we'll start with it given to us so we can practice on actually reading the table here. So this value right here, it says z, by the way, but this value right here might be 5.1 because that'd be 2 deviations down. And then you have another one here that's 4.9 because that's 3 deviations down. Now, these are what we call z-scores. So all these values down here, 5.9, 6.1, 5.7, even the 5.5 here, we usually refer to them as z-scores because they're standardized scores. So this is something you can track with any amount of label here. So if we're tracking heights, we're tracking weights, we're tracking volumes that a container can hold without breaking or something, whatever you're tracking, you can make it into a z-score style map like this. So you can compare, like we said before, you can compare values that have different units by changing them into their z-scores. If you remember back when we tracked people's heights versus people's weights and which one varied more, and in order to track which type of measurement varied more, which had more variation to it, we had to change both height and weight into some sort of standardized value, which back then we called the coefficient of variation, in order to compare how much they differ, because you track heights using feet and you track weight using pounds, at least if you're in America. And you can't really compare the change in height to change in pounds by using standard measurements there. So you had to change into a standard value, a standardized value that you can then compare because everything was normalized. And that's what z-score does here. Z-score takes a value like height, which was measured in feet, and it sort of maps it out in terms of deviation and average. So these down here would be what we use for z-scores. So 5.7 would not be what shows up. What shows up would be 1 because that's a z-score of 1 because it's 1 deviation up. 5.9 would not show up. What would show up would be 2 because this 2 stands for 2 deviations. 3 here would stand for 3 deviations. So you wouldn't see, technically speaking, you wouldn't see 5.7, 5.9, 6.1 on this z-score table. You would see 1, 2, 3. And here it'd be -1, -2, -3. So these values right here, 4.1, 4.9, 5.1, 5.3, those would be the values that are represented by -3, -2, -1, and then +1, +2, +3. Obviously, the average would have a z-score of 0 because it's exactly on the average. But that would be how this table would look here. So for instance, let me just give you a quick example here. If I wanted the, actually, let me go to the next example because then I actually have numbers to work with. So one thing you do have to know about this z-score table, though, if I go back here and change my stuff here, is that the z-score table gives you, like I said, this only works if you, let me rephrase myself here. The way you get the probabilities, you have to get them in terms of a range. I cannot ask you, if this is my height graph here, go back. If this is my height graph here, I cannot ask you what's the chance that somebody is 5.1 feet high or 5.1 feet tall. That I can't give you a probability for an exact value. You have to give me a range. Like, what's the chance somebody is between 5 feet and 5.2 feet tall? That would be a range that I can give you. Now, the z-score table gives you the probability of being up to a certain value. So let me show you an example here because I'm talking around in circles here. Let me show you what the z-score table is and how it's used in a problem here, right? So we'll start with a thermometer question. So it says a company makes thermometers and they're supposed to give a reading of 0 degrees Celsius at the freezing point of water, because that's what the freezing point of water is 0 degrees Celsius. Now, we assume that the average reading is 0 degrees, so we assume the thermometers are pretty accurate. Their average rating is 0 degrees Celsius. And the standard deviation is 1 degree Celsius. So again, if they ask you how accurate are these monitors, or how accurate are these thermometers, you say, well, they give you an average value of 0 degrees on freezing water plus or minus 1 degree. Okay, that's pretty accurate thermometer. It's not a low range of deviation, at least I think. I'm not a thermometer expert. So what's the chance that if I take a random thermometer and put it in freezing water, it would give me a reading that is less than 1.58 degrees? Well, okay, let's figure that out here. So if the average value is 0, right? The average value is 0. And I want the chance that it reads less than, so I'm going to put x as my number here. I want the chance that it reads less than 1.58 degrees. So what I need to figure out is how many deviations away from the average is this limiter value, is this 1.58? Well, if the deviation is 1 degree, so that means that each jump of 1 is 1 deviation, which is a nice deviation to have. That means that this is simply 1.58 deviations above the average. Because how many 1s are in 1.58? Well, 1.58, because 1 just goes into it, again, just one time. 1.58 times. So if you have a deviation of 1, essentially your readings are going to be your z-scores here. So we're going to start with an easy deviation to make this a little bit simpler. So my z-score that I'm looking for is 1.58. And again, why is this my z-score? Well, because that's how many deviations away my limiter value is. I want the chance that it's less than 1.58 degrees, which is exactly 1.58 deviations above the average, because each deviation I count as just one jump. So if I want less than 1.58 degrees, that means if I have my graph here, this is 0 degrees, so this is the average value. 1.58 would be somewhere right here, right? 1.58. So I want the probability that it's less than this value. So I want this area right here. I want everything less than 1.58 because this area represents that probability. And this area represents everything less than 1.58. So that probability would represent everything less than 1.58. So to find this out, I would go to my z-score table, which is right here. This is a z-score table. The way you read this table is that the side column, this z column right here, these numbers right here, give you the first 2 digits, and the top numbers give you the third digit. So you only go up to 3 digits. So if I want, well, we go back here. If I want 1.58 as my limiter value, what I'm going to do here is look at the z-score table and find 1.5, which is right there. And then I want to find 0.08 on top, which is right here. And if I go over, this right here, 0.9429, that's the probability of it being less than 1.58. Now, what I said before about this table giving you values that are cumulative to the left means that this table right here, the side numbers are your z-scores, or these parts of your z-scores. So you get the first part of your z-score on the left side. You get your third part of your z-score on the top side. The middle numbers are the likelihood, the probabilities, that your value is up to or less than that z-score. So this entire table here, these entire middle values, are probabilities that represent the likelihood of being up to or less than the z-score value. So if you wanted the chance that it was greater than 1.58, you'd have to do something with that 0.9429 value that we'll do here in a second. But if my question is less than a certain value, all I need to do is find my z-score in this table. Again, first 2 digits on the left-hand column, third digit on the top column, and then find out what that value is, which in this case is 0.9429. And then that's my probability. So if I go back here, the chance that it reads less than 1.58 is 0.9429, or translated be about 94.29%. So it's about a 94.29% that my thermometer will give me a reading that's less than 1.58 degrees if I put it in freezing water. So if you're asking a less than question, once again, you find your z-score, which is just how many deviations are you from your average, which in this case was 1.58, and then you look on your table, you look for 1.5 on the left-hand side, so 1.5 on the left-hand side, and then you look for the third digit on the top side, which is 0.08, and then you find out where they cross, and that value is your z-score. Or not your z-score, that value is your probability, sorry. Now, this one here is what I was talking about. What's the chance that it reads above negative 1.23? So if we go back and erase the markings I have on the thing here, if this is my normal curve, my average is still 0. My average value is still 0 because that's what the thermometers typically give you. Let's say negative 1.23 is like right here. Negative 1.23, just guesstimating there. I want the probability that it reads above this number, right? So I want the area above it. I want this area right here. The problem is, now again, ignore this green part here. This is just part of the picture that I found. I couldn't figure out how to get it off there, so I just left it on there. So ignore this green part here. That means nothing to us right now. But the problem with this is that my table only gives me probabilities for the left-hand side of my value. Because again, my table is a less than or equal to type of table. It will give me the chance of being less than or equal to a number. It will not give me the chance of being greater than a value. So what I do is I find this probability and subtract it from 1. Because remember, the entire curve has an area of 1, right? So that means if I take the left-hand side of this barrier and the right-hand side of this barrier and add them together, I'm going to get 1. So if I just want the right-hand side of this barrier, what I'm going to do is use my table to find the left-hand side and then subtract it from 1, and that leftover piece will give me the right-hand area. So this part right here, this area right here below the curve, that will be on the table. That's what I get from the table. And then this area right here is what I get when I take 1 minus the answer from the table. Okay? And I'm probably misspelling table, but you have to deal with it there. So if I want, let me go back to my z-scores, I just forgot it. So above negative 1.23. Now again, my average is 0. My deviation is 1. How many deviations away from the average is negative 1.23? Well, again, since my deviation is 1, it's just negative 1.23 deviations below it. Again, if your deviation is 1, then your values are your z-score. If my deviation was like 2, then I have to do a little math to figure out, okay, how many 2's are in negative 1.23? But luckily it's just 1, so I don't have to do that. We'll talk about when your deviation is not equal to 1 later on. I'm just going to stick to an easy deviation here for this example. So let me go ahead and find negative 1.23 in my table here. Where is it? There it is. So negative 1.2, and then 3 on top, because my third digit. So negative 1.23 would be right here. Come on. Right there. 0.1093. Because again, negative 1.2 on the left, 0.03 on the top, 0.1093 is my answer for there. So that would be 0.1093. Now that's the chance of it being less than or equal to negative 1.23. So if I want the chance of it being above, I'm going to say 1 minus that answer, which will end up getting me, if I do my quick calculation here, so I don't not erroneously wrong here. So 1 minus 0.1093, and I get 0.897, or 0.8907. 0.8907, which is about an 89.07% chance. So again, remember your z-score table is only for values that are below or at a certain marker. If you want a value for above a certain marker, you have to take 1 minus it. Now the tricky part comes with what if you want it between two numbers? So if I say here, what's the chance if I put one of these thermometers in freezing water, it will give me a reading that's between negative 2 and 1.5. So I don't want above, I don't want below, I want between. Well, here's what you do. You actually just do the same thing twice. So here's your curve. Let me show you how this works. Remember, your average value is 0, so this is going to be your 0 marker right here. That's your average. You want between negative 2, we'll say right here is negative 2, and 1.5. We'll say right here is 1.5. I'm going to draw my x-axis right here just so I have a barrier. So I want above negative 2, but below positive 1.5. So I want this area right here. So what the heck do I do here? How can I get this if my table only gives me the values that are up to or less than a certain marker? Well, what you do is you find the z-score for 1.5. So when I find the, oh sorry, not the z-score, you find the probability for 1.5. So when I find the probability for a value of 1.5, that will be the probability of everything up to or less than 1.5, right? So that'll be everything from 1.5 on down. Then I find the value for negative 2, which will also be everything from negative 2 on down. And then what I do is I subtract them. Because if I take the value from negative 2 on down and subtract it from the value of negative of 1.5 on down, what will happen is that everything from here will be canceled because they'll be subtracted from each other. And I'll be just left with this little marker inside here. It's kind of like having two rectangles that you subtract the areas from. So think about this here. If it was uniform, I'm not saying it is, but if it was uniform, it'd look like this, right? And here would be negative 2. Here would be positive 1.5. And then in the middle would be 0. But if I try to figure out the areas here, if I take the area from negative 2 on down and subtract it from the area, let me do this in a different color here if I can. and subtract it from the area of negative 1.5 on down, what happens is that when I subtract these two areas, this green and black area simply cancels out. It goes away because I'm just subtracting it from itself. And what's left is the area that's between the two values. So summarize here, if you have a question that asks you to figure out the probability of being between two numbers, what you do is you find the probabilities of it being both, and then subtract the smaller from the bigger. So let me do this here. So I'm going to find the probability of it being less than or equal to negative 2, and the probability of it being less than or equal to 1.5. Let me do that with my z table here. So let me do negative 2 first. So on my table, here is negative 2, and then I want 0.00, because I don't want negative 2.01, I just want negative 2. So that's 0.0228. So let me write that down here. 0.0228, and then positive 1.5. So going back to my table here, here's 1.5, and then again 0, 0. So that would be 0.9332. So 0.9332. So again, if I redraw this graphically just to show you why this subtraction stuff works, let me use my thing here. That's way as I have a pre-drawn nice little curve here. Okay. So let's say that this marker right here was negative 2, and then we have 1.5 up here. So I know that from negative 2 on down, so from negative 2 on down is 0.0228. And I know that from positive 1.5 on down is 0.9332. I'm going off the curve here just to give myself some space to draw. So don't take into account that I'm actually going above the curve here. That's just for me doing a clerical thing. So what I'm going to do is subtract 0.0228. I'm going to subtract everything from here on down from 0.9332, and that will give me what's left essentially. So I take 0.9332, subtract it by 0.228, and what I end up with will be just the area between them. So if I do that on my calculator real quick, 0.9332 minus 0.0228, we get 0.9104. So my answer for being between negative 2 and 1.5 is 0.9104, or about a 91.04% chance. So there's basically three types of questions so far that I can ask you about z-scores. Find the chance that it's less than a number, in which case you simply look up the number in the table, get your answer, and you're done. I can ask you what's the chance that's more than a value, which in this case you look up your answer in the table, you subtract it from 1, and then you're done. And then I can ask you what about if it's between two values. In that case, you look up the value for the first z-score, you look up the value for the second z-score, and then you subtract the smaller from the bigger. Because remember, your probability can't be negative, so it's always bigger minus smaller in terms of probability. So those are the three types of questions you can be asked about normal distributions so far. And again, I'm going to keep the deviation. I kept the deviation at 1 here just to make it easier to look up the values. Let me try one more here real quick. First off, some notation, by the way. So this was basically the between question. So what's the probability that's between A and B? This was the probability that's bigger than a value, and this was the probability that's less than a value. So this was just kind of restating the three types of questions you'll see here. And again, this is just basically rehashing what I just told you. So I'm not going to spend too much time on it here because I just told you it. Now, you can also be asked to work backwards. So I might ask you, okay, find the temperature corresponding to the 95th percentile. So we're still using the same values. So average was still 0, and the deviation is still 1. What if I asked you, what is the temperature that's the 95th percentile, which means that on this curve here, I'm going to try to draw the curve the best I can. On this curve here, what value, so I'll put a little x here, what value, question, is the 95th percentile, which means it's more than the bottom 95%. So 95% of the other values are below it. What's the probability that it's in that zone there? Okay, well, this is a little bit of a strange question because, again, it's asking me to work backwards. It's not giving me a value to check the probability for. It's basically saying, here's the probability, find me my value. Okay, well, if I look at this here, that means that if it's in the 95th percentile, that means 95% of the area under the curve is below it. Well, hold on. This z-score table, these values in the middle here, that's basically the area under the curve. Yes, they are probabilities, but remember, because it's a density curve, these probabilities also represent the area and vice versa. So if I'm asking essentially what value separates the bottom 95% area from the top 5% area, because remember the entire curve is 100 or 1, then all I need to do is simply look up what z-score matches a probability or an area of 0.95, because again, it's given to me in decimals here. Well, okay, so let me go here and look at my table. And I'm looking for 0.95 in the middle. So again, I'm working backwards. I don't have a z-score to find. I'm given a middle number, 0.95, and I want to work backwards to figure out what z-score fills that. So in this case, I'm going to look and try to get as close as I can. So 0.95, 0.95. Well, here's 0.938, 0.939. Keep going here. Here's 0.952, so that's too much. So right here. So unfortunately, it doesn't give me an exact value. It gives me 0.9495 and 0.9505. So both of these values right here are a little bit off of my 0.95 that I want, because I want 0.95 exactly. I don't want 94.9%. I don't want 95.05%. I want exactly 0.95 or 95%. Now, in this case, what I would do is give my best estimate. So it's going to be somewhere between 1.64, because here's 1.6. It's going to be somewhere between 1.64 and 1.65. Now, if you have another table, most z-score tables give you critical values down here, usually below the table, and these critical values are simply common values that occur in stats. And luckily, 95% is one of those common values. And we'll talk why it's a common value in a further lesson here. But if you have a more advanced table, it will tell you down here that 0.95 actually has a z-score of 1.645, which is basically halfway between 0.04 and 0.05, which can be understood there. So the actual answer for this would be 1.645, would be both the z-score and the temperature value, because again the z-scores and the temperature value here are the exact same because you have a deviation of 1. But this would be the temperature that's in the 95th percentile. So the temperature of 1.645 separates the top 95% of values from the bottom, or sorry, the top 5% of values from the bottom 95% of values. So again, it sounds kind of complicated, but it really is just you're reading the table literally backwards. Because if you remember in the last question, we were given a z-score. Like, what's the probability that it's 1.5 degrees? So we were given a z-score, and we looked up the probability. And all that's happening here is that they're giving us the probability, and we're looking up the z-score. So we're just reading the table from the inside out rather than from the outside in. And you can probably guess that when we're asked about the between values, we do something very similar to what we did before. It says find the temperature separating the bottom 2.5% and the top 2.5%. So if this is my curve here, right there, the bottom 2.5%, so here's my first value. So here's question. Bottom 2.5%, 2.5%, and the top 2.5%. So another value here, the top 2.5%. So I want to know, what are these two values? Well, like before, I'm going to look up two different z-scores. I'm going to look up the z-score for the bottom 2.5%, and I'm going to look up the z-score for the top 2.5%. Here's the trick, though. For this value right here, remember, your table only gives you probabilities and percents for stuff that's less than a value. So if I want to look for what value represents the marker for the top 2.5%, I'm actually going to flip that and ask what value represents the marker that's above 97.5% of the rest of the data. Because if this is the top 2.5%, that means from this value on down is 97.5%. So again, if you're looking for values that are on the right-hand side, you have to change them to left-hand side values by using that 1 minus trick. So 100%, minus 2.5% gives you 97.5%. So again, your table only gives you left-hand side values. It only gives you less than values. So if you're asked for a more than question, you have to change it to a less than question by doing that 1 minus or 100% minus whatever percent. So let's do the bottom 2.5% values first. Let me call this x and call this y, just so I don't have to keep drawing questions. So if I want to find the value of x, that is less than 2.5%. And I shouldn't say less than, I should just say bottom 2.5%, but less than seems to be easier to trigger people with here. So we'll say bottom 2.5%. So I'm looking for 0.025, because if you didn't remember, 2.5% as a decimal is 0.025. So that's the probability I'm looking for. So 0.025, 0.025, 0.025. Let's see if I can't find that in here. Here's 0.028. That's too much. 0.024. So right here. Exactly. 0.025. So what z-score does this represent? Well, if I go over here, it represents negative 1.96. So this would be negative 1.96. That would be the z-score, or the temperature in our case, that represents the marker for the bottom 2.5%. So 2.5% of my possible temperature probabilities are below negative 1.96. Now, if I wanted the above values, again, to go through the logic here, if I wanted above 2.5%, or the top 2.5% rather than not above, but the top 2.5%, that means I'm looking for 0.975, because this is the lower end probability, and that's going to be what shows up on the table, not the high end probability. Now, luckily, if you're looking for a symmetric split, like bottom 2.5 and top 2.5, one of the key aspects about a normal curve is that it is symmetric. So that means that if this value is negative 1.96, the same value on the opposite end is going to be positive 1.96. Because again, it's symmetric. So if the negative 1.96 cuts off the bottom 2.5%, then positive 1.96 will cut off the top 2.5%. So this value is just going to be 1.96. Now, if I said the bottom 3%, then I have to go and figure that out the long way. Which, just to prove my point here, if I look for 0.975 in my little chart here, 0.975, let's see, where are you? Right here? Oh, no, it's 0.9975. I want 0.975. Right here, 0.975. Well, it's 1.96. So as I said, it's the exact same value, just on the positive end there. So if you're looking for a between two percentages sort of idea there, do remember that if you have the same percent on top and bottom that you're cutting off, then it's just going to be a symmetric answer. Positive one side, negative the other side. And that's how you would figure it out. And usually, as I said, because the table is already given to you in less than terms, the table already gives you probabilities that are less than a certain value, you're usually easier to find out the negative number first and then just copy it for the positive answer. So figure out the negative version is easier than figure out the positive version. So that's it for this video here. I know it's a lot to take in because this z-score is really a different way of thinking, but it's one of the key concepts that we're going to have in stats here. And that's why we're going to spend some time practicing this stuff here. There's another lesson coming up here that will teach you how to, again, further expand on this when there's not a clear-cut deviation of 1. Like, let's say my deviation was 2 instead of 1. In fact, just to give a quick little aside here, doing the best I can, let me get to a screen that I had before. I can't find it. Let me just use this screen right here. Let me blow up this image here one more time. So let's say my deviation wasn't 1. So if I erase this here as best I can, let's say that instead of being an average of 0 and a deviation of 1, let's say I had this case where I had a normal distribution. But let's say I'm tracking, again, let's say, I don't know, the weights of certain rubber balls or something like that. Let's say that the average weight ended up being, I don't know, 12 ounces, and that the deviation was a deviation of 2 ounces. Well, that means that if I'm looking for the z-score of a value for a weight that's, let's say, less than 13 ounces. So I want the probability that if I take one of these rubber balls, if their average weight is 12 and they have a deviation of 2, what's the chance that I pick a rubber ball that has a weight of 13 ounces? Well, how many deviations above the average is 13 ounces? Well, it's 1 ounce above the average, which translates to half a deviation. Because the deviation is 2 ounces, 1 ounce, that's 10Z, not 10. Let me try and make that ounce smaller so I know that it's an ounce, not a 10 there. So that means that 1 ounce translates to a deviation change of a half, because 1 ounce is half of 2 ounces. So remember, your z-score isn't always just simply the value you're tracking. Like, this wouldn't be a z-score of 13. It's how far away from the average are you? If you're 13 ounces and your average is 12, that means you're 1 ounce away. Well, how many z-scores is that? Well, if your deviation is 2, 1 ounce is half of that, so it'd be 0.5 deviations above the average. And again, we'll talk about this in a later video about how to track these items here. But that's the idea. So don't think that z-score is simply the value you're checking. Z-score is how many deviations is the value you're checking away from the average. Again, feel free to review this video too if you have trouble doing it. It takes a while to sink in, takes some practice there. We'll talk about it in class as well. If you have any questions, If you do have any questions, let me know. Otherwise, have a good day, night, or afternoon.